Okay, so I want to show you guys a particular type of problem that we've seen 4 times now, twice on today's sort of review as the limit-based continuity worksheet. This is the first, what I'm showing you right now is the first time we saw it. And this is in our Unit 1 notes packet. This is on page 18 of the Unit 1 notes packet. We had a problem like this where you have a piecewise and it's asking you to find values of 2 missing variables, not x, but this a and this b here, that would make k of x continuous. Okay, and so here's the first time you see it. Okay, and then the next time I mentioned it was when we were doing the skill builder for 1.11 to 1.13. Number 6 on page 4 of that, number 6 on page 4 of that is the same type of problem. And I referred you back to example 4 from the notes packet and pointed out that that is shown in the video, which I believe was posted yesterday. I'm not sure. But the video that goes with the notes packet for 1.14, actually yesterday, 1.13 maybe. Let me find the video for you real quick. But I referred that to you and said, look at this, make sure you look at him, watch his notation as he completes number 6 and model your solution as close to his. So the point is, I'm not going to find it, you guys can find it, is that this is that same type of problem that we are looking at here now on this particular worksheet. And it's problems 6 and 7. Excuse me if I'm making you seasick. They're both that same type of problem where it gives me a piecewise function and it says make it continuous, and we have variable values other than x to figure out what m and what k would make this continuous at those places where we jump from one rule to the next, basically. Okay, so the way this is put here is meant to sort of walk you through the process. And I think some folks are getting kind of hung up on this wording, but really it's about trying to make it easier for you. So I want to do number 7. Number 7 is the same idea as that video. And I would strongly suggest going back and looking at what he does, because he was modeling that exact same type of problem for us. We did it in the notes together, but I like his better. He's just pretty cool. So let's look at this. It says, consider the function g of x to the right to answer the following questions. What 2 limits must be equal in order for g of x to be continuous at x is negative 2? X is negative 2, and I'm going to play with the lights here a little bit. Okay, that x is negative 2 means I want a smooth transition from here to here. I want these two to come right up to each other so that they're both approaching the same thing from either side. Okay, so the 2 things I need to happen in order to make it continuous at negative 2 is I need the limit approaching negative 2 from the left of g of x to equal the limit of x approaching negative 2 from the right, but of g of x. But I really don't even care about this notation, because in this particular case, g of x means different things, different places. So we really need to be more specific than that. This is true anytime you're doing a piecewise, you're doing a one-sided limit on a piecewise. You need to be specific about what are you plugging in. What I'm looking as x approaches negative 2 from the left, I'm looking at what expression here, because these mean different things. It's like somebody wearing a costume in different locations. He's Superman when he's saving the world, and he's Clark Kent when he's at work. So really what I want to see here is the limit as x approaches negative 2 from the left of, this is x is less than negative 2, so that's when x is to the left of negative 2 of that expression. I need that to be equal to the limit as x approaches negative 2 from the right, which is happening right here. Okay, these are when we're at negative 2.0001, we jump down to here. So that's of 4x plus 1. So that's what they're asking me, is what 2 limits do you need to be equal for that to be continuous? That's what we need. That's basically, those are the 2 limits we need to be equal in order for there to be a limit at x approaches negative 2. Then the next thing is just asking me the same idea about over here at 3. Sorry, the hole is right there. At 3. So in other words, I'm trying to adjoin these two pieces, make them approach the same thing when x is approaching 3. So my limit as x approaches 3 from the left, and that means I'm using this because this is true when x is less than 3. Okay, so of 4x plus 1 has to be equal to my limit as x approaches 3 from the right of kx minus m. Now, let me just jump away from this for 1 second to point out, I'm seeing a lot of people struggling to write limit notation in the very general sense, okay? If you know how to write, I don't know, log base 3 of something, and you know how to write sine of something. In other words, we don't just ever write sine equals this. We write sine of theta, sine of A, sine of 39 degrees, whatever, sine of pi over 6. Then you know how to do a limit, meaning it's always, we don't ever, ever, ever have this equals something. You have to have of what, the limit of what in there. So there has to be something between your limit expression and the equal sign. It's the limit of such and such is equal to this. Okay, so make sure that you're not just writing the limit equals, because you have to have the limit of whatever. And in this case, we even want to go more beyond, we want to go beyond the specificity of just saying g of x and say which part of g of x, because we're going from different sides, and that means different parts apply. Okay, so determine the values of m and k so that the function is continuous everywhere. Well, everything else here is continuous on this interval because that's a polynomial. It's continuous on this interval, polynomial, polynomial. The only places we could have discontinuity is at -2 and at 3. So that's what we're looking at. We want this to be true, and we want this to be true. Okay, so I'm going to write at x equals -2. What I need to happen is I'm just going to rewrite what I said up here. I need the limit as x approaches -2 from the left of k x squared plus m to be equal to the limit as x approaches -2 from the right of 4x plus 1. And then I'm going to start figuring out what that limit is. We can plug in for this x here. If we're approaching -2, if that's the whole idea, then this with a polynomial, I could just plug this in. This is k times -2 squared plus m. And over here, this is 4 times -2 plus 1. Remember, it's x that's approaching -2, not k, not m. So you got to plug in for x, nothing else. So this is 4k plus m equals -8 plus 1, so that's -7. So that's one equation that I got from looking at the continuity that needs to happen there at x equals -2. Okay, I have two variables, so I need two equations. That's where looking at what happens at x is 3 is going to come in. Any questions or comments or things I've left out so far? You guys okay with where we are now? Okay. So the limit as x approaches 3 from the left of 4x plus 1 has to equal the limit as x approaches 3 from the right of kx minus m. So again, I can put that positive 3 in there and say this is going to be 12 plus 1. This is going to be 3k minus m. Remember, we're plugging into x. So 12 plus 1 is 13 equals 3k minus m. And now I have my two equations and two unknowns, which I can create a system of equations out of to be able to find k and m. Okay, so let's do that. I'm going to put alphabetical order, k before m. Putting them together in a system. All right, the easiest way to solve this system is elimination because we already have one of our coefficients or the coefficients of one of our variables being opposites. So I can add them together, top to bottom, and I get 7k equals 6, k is 6/7, and then I can go plug in 6/7 wherever I want to find m, like right there. 13 equals 6/7, 3 times 6/7 minus m. So this is 18/7 And 13 is 91/7. I found that out by multiplying 13 times 7. Minus m, subtract 18/7 from both sides. And I get 73/7 equals the opposite of m. Divide both sides by -1 or multiply both sides by -1 and you get m is -73/7. So those are the values of k and m that will allow my left-hand limit and right-hand limit to match at -2, and my left-hand limit and right-hand limit to match at 3 as well. And that's what we're doing for all of these. Key thing about notation here is that you do need to plug in what is it you're using, what are you plugging the left-hand limit into, and what are you plugging the right-hand limit into. Okay, and those vary depending on what you were told about where each of these expressions applies. If you're to the left of -2, it's this one. To the right, it's this one. All right, I think that's about it.